Mm. Numerical analysis of the effect of anisotropy local turbulence on the static pressure fluctuation characteristic. I'm Naoki Kobashi from Local University. Numerical simulation has become a major tool alongside experiment theory. It is fast and safe and cost-effective, allow us to explore parameter and that are difficult to access experimentally. Turbulence is ubiquitous in both everyday life and engineering system. Accurate prediction and control of turbulence are essential in manufacturing, transportation, and energy applications. Previous studies have contributed to our understanding in several ways. Wall pressure structure have been analyzed by Anonsalam and Hemash and Suzuki et al. Earlier study have evaluated the effect of anisotropy, control and conservation errors. Additionally, turbulence errors under special conditions such as MHD flows, weak acceleration, and fractal grid generation turbulence has become investigated. Despite these advances, prediction pressure fluctuations remain difficult. Small error in conservation or resolution can strongly affect RMS level and correlations, especially as the anisotropy increases. Pressure directly participates in the velocity, production, and dissipation, making this even more critical. The objective of our study threefold. First, to quantify the response of the static pressure fluctuation in anisotropic turbulence. Second, to clarify their relationship with intercomponent energy transfer. Third, to conduct areas with conservation preserving, preserving discretization while continuously varying anisotropy. To achieve this, we employ a tunable forcing scheme to generate a wider range of anisotropy turbulence fields. We measure turbulent kinetic energy and pressure, evaluate pressure RMS and spatial autocorrelation, and propose a quantitative indicator that can support model development and practical applications. We analyze force homogeneous incompressible turbulence in cube with triple periodic boundary. The governing equation are the continuity equation and the Navier-Stokes equation with the external forcing term. LES is used separating each field into grid scale and subgrid scale components. Special derivatives use fourth-order central differences and time integration employ a six-stage fourth-order Runge-Kutta scheme. Pressure velocities coupling is solved using a fractional step method, ensuring stability under both its isotropic and anisotropic conditions. The forcing is theta type and controlled by the voltage scale parameter M and the anisotropy parameter A. A equal 1 give us isotropic field, while A not equal 1 introduced anisotropy. The CGS model is Smagorinsky with CS equal 0.1. The subgrid is 32 cubed. The time step is delta T equals 0.002 and integrations plus C's to non-dimension time t equal 3000 and as trophy is swept over a equal 0.5 to 1.5 to evaluate the statistics of pressure fluctuations. The time evolution of three-dimensional velocity fluctuation intensities is shown for anisotropy parameter A equals 0.7, 1.0, and 1.3. For A equals 0.7, 1.0, and 1.3, the time series of U square, V square, and W square exhibit a transient stage for t less than 200 and reach and statistically steady regime for t greater than or equal to 100. A red line indicates the mean over t equal 200 to 3000. In all cases, a steady state is achieved for a equals 0.7 and 1.3, and the mean of the component differs systematically from those of the y and z components. Confining and anisotropy is correctly imposed, whereas at a equal 1.0, the three dimensions coincide as expected for isotropy. The upper figure shows the visualization of turbulent kinetic energy, and the lower figure shows that of static pressure fluctuations. Ice surface of TKE near the mean value, of static pressure fluctuation on the negative side of the mean at a resolution of nx equal 32 exhibit direction, free vortex structure, and isotropy. In anisotropy in cases, the large-scale morphology remains bloody, similar to the isotropy case. Negative pressure region appears a vortex tube with visually filamentary connections. Within the exposure range of A, anisotropy has only a modest first-order influence on the spatial structure of TKE and pressure. The upper figure The left figure shows the time evolution of turbulent kinetic energy, and the right figure shows that of the static pressure fluctuation RMS. The stationary average TK reach statistically steady state for t greater than or equal to 100. It means amplitude and dominant periods are nearly identical across all anisotropy parameter A, indicating the primary time response is only weakly affected by anisotropy. The RMS static pressure fluctuation shows similar behavior for A equals 0.7 and 1.3. Both the mean and amplitude closely match the isotropic difference. A joint inspection of the two times series uh, reveal the phase relationship between energy input dissipation and pressure dissipation is stably maintained with no significant bias introduced by the SGS model or numerical discretization. Reference line at 1.0 Gaussian autocorrelation and 0.5 exponential autocorrelation aid interpretation. The relative intensity decreases graduation as a departure from unity, consistent with slow decay of correlations at large separations. Where the relative intensity drops, vortex structures persist long and long wavelength. Content become comparatively more prominent. To disentangle contribute, we examine time average TKE and pressure RMS over A equals 0.5 to 1.5. Relative to the isotropy reference line, K change little with anisotropy, with a slight increase at stronger anisotropy. To examine the contribution to the relative static pressure fluctuation intensity, turbulent kinetic energy, and the pressure RMS and the property as a function of the anisotropy parameter A, and the pressure RMS shows no significant change and exhibits a slight decrease on the strongly anisotropic side. Overall, the impact is small for A equal 0.7, 1.3, with larger deviations observed outside this range. The sensitivity of the pressure RMS to anisotropy is smaller than that of TKE, suggests that Arias' prediction of the pressure statistics remain comparatively robust under the present forcing anisotropy. Conclusion: to delineate response of the static pressure fluctuation to control anisotropy in statistically steady turbulence connecting amplitude change timescales and structural signatures. Using Forsen method with continuously adjustable anisotropy, we generate flow ranging from isotropic to anisotropic and obtain consistent statistics and the time response of velocity and pressure field areas with conservation response respecting, respecting discretization. The pressure RMS is less sensitive to anisotropy than decay, suggests that within practical range of A equal 0.7 to 1.3, areas can maintain robust pressure statics and the pressure forcing design.